Hello everyone and welcome back to the channel. In this video, I want to show you the complete flow of our minimal embedded database system. And by embedded, I mean that the current design of the database does not support running as a standalone process. The project is called Testudo, and you can find the source code on GitHub. So like always, feel free to check out the code and ask questions through YouTube comments or GitHub issues. So let's see what we have covered so far and what we have not. I will review each of these topics quickly before we move to the complete flow. And the flow that we will talk about today are database operations. We have covered index management and indexing, which includes algorithms such as B+3 and combination of B+3 and list, which in my case I used array list and bitmaps. We have covered index storage manager, file handler pool, caches and mostly LRU caches, reader-writer logs, and schemes, which I have discussed very briefly, and finally database storage. On the other side, we haven't still covered topics such as serialization, queries, and database operations. In this video, I will briefly talk about all of them as well, but I will create new videos to cover each of them separately in more details. At some point in the future, we may also visit parsing and client-server model as well, but since the library is meant to be used embedded, that is not our focus right now. So we began everything from indexing and index management. In a database system, indexing is a mechanism that helps us find the data that we are looking for more quickly than looping over all of the available data. For unique indexes, we use B+3s. It's a balanced tree, which also maintains order of the keys. And for non-unique indexes, where duplicate values are allowed, we have two options: B+3 combination with lists and bitmaps. The values in all cases are cluster IDs, which is explained in episode 10. Also, you can see related episodes to each of these topics in the box at the right side. Then we have index storage management, and we discussed how indexes are stored on disk and how we can track multiple B+3 nodes and the root of the tree. We also discussed different ways of storing indexes into a single or multiple files, which also changed over time. Next, we have file handler pool, which is a pool of open file handlers that supports limiting the number of open files. And in Java terms, this is a pool of open asynchronous file channels. All file requests should be requested from the pool, and using an attribute, we track the number of usages per each file as well. Next, we have briefly understood usage of cache in indexing. We have discussed storing some B+3 nodes in LRU cache. Also, we have seen usage of reader-writer logs in multi-threaded environments, but we will be back to both of these topics later since their usage in the project are a little bit different than what we have discussed so far. In episode 9, I have mentioned schemes. A scheme is like a database definition. It can be stored as a JSON format into a file, which will be loaded during the database initialization. We can have a list of collections per each scheme, where each collection has a name and some fields, and fields have different types and maybe index as well. A field can also have some metadata, like a comment, max length, which is useful in some field types, and a char set for strings. Next, we have the database storage, which its theory was covered in the last episode. We use page buffers and store objects into the disk and retrieve them back using pointers. LRU cache is also used here as well, and we have discussed it too. Now we move on to some of the topics that are not covered yet before we put all of the pieces together. Our first new topic is serialization, which is the process of converting an object to byte array and creating an object from byte array. Since each field type has a serializer class registered for it, We can also serialize a full object, such as an instance of a collection object, or what we traditionally know as a database model or entities. So let's see a little bit of code and see how it works so you have an idea about it. So here you can see that we have a class named model, and this class represents a collection called test, and it has two fields, integer ID and integer count. And each field also has an ID, which in my implementation of schemes, we have to set IDs for fields. And we could specify a type for the field as well, but it actually understands that the type is integer from the Java class. And before we see how the serialized byte array looks, let's see the serializers. In the serialization package, we have a serializer registry, and we have some serializers registered by default. So the idea is that if you later want to add new types to the database, you should implement an serializer for it and register it in this registry. And here you can see that we have integer serializer registered. These methods are part of the interface serializer, and we are overriding them here for integer serializer, as you know. So we have to determine the type of the serializer, which in this case is integer class, and the type name is coming from the field type int, which is still int. And down here we have methods like serialize, which takes an integer and a meta object and has to return byte array for this integer. And right now we use guavas to byte array a static method of ints class. And we also have a method called deserialize, which takes a byte array and has to return the integer. Another important method here is getSize, which determines the size of the byte array for the serialized object. So in this case, we have integer.bytes, which is 4. So if we come back to our example, the most minimal thing that we can do here is to find the size of the byte array that we need for this model class. Since it has two fields, which both are of type integer, and each integer requires 4 bytes, then we need 8 bytes for this model class. So the simplest thing that we can do is to serialize ID, which is the first field based on the ID of the field, and store it in the first 4 bytes, and then serialize count, which is the second field, and store it in the second 4 bytes of the model class. So let's run this code and see how it works. So we have a model 1, which the serialized version looks like this, and let's see what it was in model 1. Here we have created it, the ID is 1 and the count is 2. And then we have serialized it, and using the hashcode class, we have printed the serialized version. So each of these two integers show a single byte. And you can see that the first 4 bytes show number 1, which is the byte representation of integer number 1. And the second one shows number 2, which is the byte representation of integer value of 2. Now let's also change it for the second model. And you can see that the first 4 bytes are for integer ID, which the value is 5 here, and the next 4 bytes are for count 9. In case I change the order of these IDs, the placement of their values should also change in the byte array. And I don't have to even start from 1 and 2, they could be any numbers. So let's set this one as 10 and this one as 5. As you can see this time, the integer value of 1 for ID 1 in model 1 is in the second 4 bytes, and the count is at the first 4 bytes. So this is the base idea of the serialization, and we will cover more details such as serializing nulls and deserializing and much more in next videos. Next, we have queries. Queries will basically filter the data that we want to select from a collection. Additionally, I use them for offsets and limits as well, but we will see these details in future videos. Queries also support operations such as greater than, smaller than, equal, like, and much more. And as you may have guessed it, queries use our index managers. And if you go back to older episodes, you see that our index keys should all implement Java's comparable interface, which helps here. Finally, we should know that the result of a query is an iterator of cluster IDs. So at this point, we want to put all the pieces together. I want to quickly show you the process for two of the main database operations, inserting and selecting. Note that the process shown here is for a very minimalistic database, which only is made for educational purpose. Advanced databases will probably do a lot more than this. Also, as always, there may be some changes applied to the process in the future, meaning that I can be a little bit wrong about some parts, and in that case, place a comment under this video. I will update you if I spot these changes later on. Our first operation is insertion. Inserting into the collection starts with locking the collection. We will use reader-writer locks to lock the collection, as we have discussed in previous videos. And of course, we need to store these logs somewhere, so we need a map of a collection to logs. And without this locking, our indexes will get messed up easily, especially in multi-threaded environments. Next, we need to determine the cluster ID. Every cluster ID should support incrementing. So we can grab the last value of the cluster ID and add 1 to it. Of course, here we use unique index managers because cluster IDs should be unique, and a b+3 will be used. And since we are talking about sticking the pieces together, you should also remember that the index file will be added to the file handler pool. Finding the last cluster ID is also quick because b+3 is ordered, and cluster indexes use LRU cache as well. After that, we go for the serialization. So we should convert the object that we want to store into the database to a byte array. Next, we have data storage, and again, file handler pool is used to access the DB file. Here we use page buffers as well to improve the overall performance. And after we store the data on disk, we have a pointer to where the data is stored. Our next step is to store the cluster index, which means that our key in the cluster index is the cluster ID determined in the second step, and the value is the pointer determined in the previous step at data storage. After that, we store the field indexes. And to do that, we use the scheme. We find all of the indexed keys and add these keys to a proper index manager. Finally, we can unlock the collection. Unlocking is basically like try and finally blocks. We should unlock the collection if any step fails as well. Also, we could move the serialization to the first step and then lock the collection, because serialization does not require collection locking, and in this way we can reduce the time that the collection is locked. You should also note that this whole process is not fail-proof. If any of the index storage steps fail, we will have a corrupted database. If the data storage step fails, well then we have an object on our disk that is not pointed to anywhere, but if storing cluster index or storing field indexes fail, then things will go wrong. And obviously, transactions are not supported yet as well. Now let's see how selecting the data from database works. Like before, our first step is to lock the collection that we want to select from. And this time we lock the reader lock of the reader/writer lock. And you can look up the concept of reader-writer locks to see why and how it works. After that, we execute a query. So we will filter the requested data, apply offset and limit. If there are no filters, we of course get all of the cluster IDs, but otherwise we only get iterator of cluster IDs that we wanted to filter. So this is basically like the where clause in traditional SQL queries. And after that, we have to wrap the iterator of cluster IDs by looking through the cluster index and find pointers per each cluster ID. So eventually we have iterator of pointers. This means that when we call the next method of the iterator, it will go over the cluster index manager and look up for the cluster ID and grab the pointer of that cluster ID and returns it. Next, we have data storage lookups. What we do here is to wrap cluster pointer iterators from the previous step with a new iterator, and when we call next method of this new iterator, we grab the byte array from data storage using the pointer. Then comes the deserialization. We again wrap the iterator and we convert the byte array returned by the next method of the iterator and deserialize it into the accepted object. And finally, we can convert the iterator to list and unlock the collection. Or we could create a stupid unlockable iterator, so the user can iterate over the iterator as long as they want, but then they have to unlock it manually in the end. So note that nothing is read from the cluster index manager to data storage and nothing is deserialized until the next method of the iterator created at the execute query step is called. In other words, only at this step or this step we are actually hitting the database by calling the next method of the iterators. Before that, we have this giant iterator that follows this complex pipeline of executing the query, doing a data storage lookup, and deserialization. So that's it for this video. And the topics that we haven't covered yet are now limited to parsing and client-server model. We have talked about serialization, queries, and database operations like selecting and inserting in this video. If you have any questions, leave down a comment. Don't forget to subscribe to the channel. And until the next video, take care.